Hello, everybody. I'm Phil Lamar, and I want to welcome you to NASA's Ask the Astronomers Live, where we have live astronomers here to answer your questions about the universe. Now, you can ask questions of our scientists today in the comments section at our Universe Unplugged website, where you can also find out about upcoming shows and see lots of fun astronomy videos. That's at universeunplugged.org. And if you do ask a question for our scientists today, make sure to include your social media handle, and hopefully I'll pronounce it right. All right, today we are talking to two astronomers who use the gravity of clusters of galaxies to peer into the farthest reaches of the universe. Pretty impressive, huh? And I don't even know what it means, but let's find out. We are joined today by Dr. Lou Strolger from the Space Telescope Science Institute. Hey, Lou.
Hey, Phil. Glad to be here.
Oh, thank you for being here. And can you please just tell the folks who are watching a little bit about yourself and the stuff you do?
Sure. So my name is Lou Strolger. I am an observatory scientist and the deputy head of the Instruments Division at Space Telescope Science Institute. That's what I do by day or for most of my job. But the other part of my job is research. And the research that I do is trying to understand the nature of supernovae and what those supernovae can tell us about the nature of our universe. And sometimes those supernovae happen behind clusters, and that's quite a great thing for looking at even more distant objects and looking at more distant supernovae.
And just for anybody who's not a big comic book head like me, supernova, those are exploding stars?
Yes, they're stars that end their lives in an explosive way, one way or another. And when they do, they're extremely luminous events that can be seen halfway across the universe.
Wow. Well, maybe we'll get more into that. But first, let's say hi to Dr. Dan Coe. Dan
Hi,
is
thanks for having me, Phil.
Space Telescope Science Institute. Hi, Dan.
Hi, good to see you. Thanks for having me. Look forward to answering everybody's questions. And so I also work at the Space Telescope Science Institute. It's a great place. Lou and I aren't your typical astronomers. Most of our colleagues our age are professors at some university. So they do science and then they teach and have other duties. But we, instead of teaching, we support the Hubble Space Telescope and other missions. So the Hubble's been up there for 30 years now. I've been working on Hubble images for 20 of those years, and I've been here in Baltimore for the past 10. And I've had the privilege to work with Lou. We've teamed up on a lot of large Hubble programs.
Wow. Okay. That's fascinating. And Hubble has been up. I didn't realize it's been up for 30 years. But then again, I'm at that age where everything that seemed like last week was like, oh, that's 40 years ago. Oh. And things that are old and far away. Let's talk about the universe. Now, we're talking about clusters of galaxies that act like lenses and help you guys see things incredibly far away. How is that possible? How can a galaxy be a lens?
Well, so it's really gravity. So what gravity does is it pulls on the fabric of space-time, and that pulling on the fabric of space-time distorts it in such a way that it distorts paths of things trying to go around it or nearby it. So light itself will get bent by that gravity and sometimes right back into the line of sight of an observer here on Earth or on the Space Telescope. This bending of the light does two things, as bending of the light would in a piece of glass. It can magnify that light, and it can also cause a distortion of that light. We use both properties, in fact, to learn both about the nature of the things that gravitate inside of clusters of galaxies. Most often, we're talking about ordinary matter and dark matter. And we also use that as a tool, as a natural lens, to magnify even further objects and learn more about the more distant universe.
Oh, interesting. So wait, when you say it distorts light, and as well as bending it, does that mean it might change the image you're seeing? How do you account for that?
Dan, do you mind if I bring up your wine glass image? Is that all right?
Yeah, absolutely.
All right. So image number 2, if you don't mind. So this is an example of what a piece of glass would do in distorting the image that it sits behind it. You can see the candlelight in the background and this wine glass, the stem of the wine glass, being brought in front of it. And you can see how that changes how we perceive that background light. In some areas, it gets magnified, gets brighter, but in almost every area, it gets distorted. It looks very different. And this same thing happens with the nature of gravity. By changing the light path, or changing the path of things, the light around that comes from behind it, we see objects behind our gravitational lenses, that distort their background sources. So if we can bring up image number 1, we can see the comparison. Whereas what we normally would see is this background galaxy that's seen in the upper middle part of the image. The lens, the bright yellow galaxy in the foreground, is acting, is using its gravity to distort that image. In some places, magnifying it, and others, or almost everywhere else, distorting its picture.
Fascinating. So the gravitational pull of these galaxies bends the path of matter and light.
That's correct. So as matter moves around, it bends its path due to gravity. But we don't really see that as much in these gravitational lenses. What we're actually seeing is the distortion due to light. And I'm glad Dan brought his wine glass. He's got a.
Yeah.
Well, is this part of the show, or is this?
That's right. It's always wine o'clock somewhere in the galaxy.
We see the same type of effect. I can move this across one of my favorite Hubble images of the Carina Nebula, which is very close to home in our own galaxy. And you can see some of those stars. You see the multiple images. You see they're magnified, and that helps us see much more distant objects than we would be able to otherwise.
And wow. And Dan, you work on this lensing effect other than with the wine glass?
That's right. So normally I work on clusters of galaxies. Let's show that video actually that shows how this works. So as Lou said, this is Einstein's theory of relativity, that mass bends space and then light follows these curvatures in space-time to us. You can take multiple paths and the light gets focused to us. So we see these magnified multiple images of these distant galaxies. So we're able to see them in more detail. Here's a galaxy cluster. If you put it in front of a normal Hubble image, you see these galaxies a lot brighter than you would otherwise.
Oh my gosh, that's incredible. So it's just an amazing concept that you can put something in front of what you're trying to look at, and it helps you see it better.
Right.
Well, although I guess that's what telescopes are.
It's what glasses are. Yes.
We have a couple images of that, the image 5 that shows one of the most massive structures in the universe. This is a massive clusters of galaxies. And this was a daring new observation program with the Hubble Space Telescope. Typically, we had looked at blank fields and we'd stared for days on end to try to find the most distant galaxies. And there was a new program called the Frontier Fields that stared at galaxy clusters. Well, there's a lot of stuff in this galaxy cluster in the way between us and the more distant galaxies. But because of the lensing effect, we actually win and we can see more distant things. So then if you go to the next image 6, I've highlighted some of these distant galaxies that to the trained eye, you might have noticed, that some of these galaxies actually repeat. So the orange one, for example, you can see very clearly a few times across the image. Sometimes in yellow, you see that arc that's stretched apart, stretch across the image, and you see multiple images there. And then in the red, you see a very distant galaxy that's small. You can probably hardly see it, but we're able to see it thanks to this lensing effect. And that's the main thing that I do.
Wow, that's incredible. Now we've got some questions here. Some of these are from the audience. Lou, have you?
Yeah.
Because we were talking before about supernovae. Have you ever found any lensed supernovae?
Yes, this is where it gets this is where I get involved. I typically had been looking at these deep fields and then became more interested in these lensed areas when we found that we can use the lens to find distant supernovae, and in turn do some of the things that I was talking about before. We can actually use the supernovae to learn about the cluster or to learn about the nature of the expansion of the universe. One of the key objects that got me clued into this, if we can bring up slide 7, I can show you, is this event. So again, this is another cluster from the Frontier Fields program. And what we're seeing here in the inset is a single supernova that appears 4 separate times, lensed by this foreground galaxy that is, this elliptical galaxy. It's providing what we would call a perfect Einstein cross. Let's not get too much into the nomenclature here, but there's four images of the exact same supernova, and what's really cool about this is that the lensing galaxy is actually a part of this cluster of galaxies that you see mostly in yellow in this foreground image. And because of that, the cluster is also multiply imaging the host galaxy of the supernova. So not only do we see those 4 individual images of the supernova, we actually had other opportunities to see the same supernova go off in other areas of the same image. You can see where the galaxy appears in the blue circle in the upper left. You can also see where the galaxy appears just off the center of the cluster. And if we had been staring at this cluster back in '95, we might have seen the supernova. But this also allowed us an interesting test. We could, because of the way that the light has to travel both through the cluster and around the gravity, the timing of when these different images arrives is actually quite interesting. The 4 images in the foreground were separated by days, but we could use the nature of the cluster to predict when the next image should arrive, the next supernova image should arrive. We predicted it would arrive in that galaxy highlighted in red sometime in the time frame of 2015 to 2020, with a really strong guess that it was around 2015. We actually scheduled time to do that, and lo and behold, the supernova did reappear almost a year to the date after the discovery of the first 4 images. So it was the very first observation of a supernova that was predicted to where we knew where the supernova would occur and when. It's a really cool discovery.
That's great, great. Dan, what about you? What have you seen with the lensing that you work with?
Right, I wanted to mention that what Lou just talked about was especially exciting for me. One of the main things I do is to map out all of the dark matter that's in these galaxy clusters. What we see is only 1% of the mass that's there, and we need to use this lensing effect to figure out exactly how much mass is there and where it is. And what Lou just described was really the only way that we've been able to test our predictions of where the dark matter is. And like we said, the modelers did a really great job, and it seems like we have a good idea where the dark matter is. And then I'll show you the one highlight of what I've worked on in image number 3. So this was what I discovered 7 years ago, was the most distant galaxy known. And it's currently number 2. It's about the same distance as the current record holder, but we're looking 97% of the way back to the Big Bang. We're looking back in time to when the universe was only 400 million years old. And here again, we see these 3 magnified images of a distant galaxy that it would have been very hard to see without gravitational lensing.
Interesting. And was that a Hubble image?
That's right. Yeah.
Okay. That's wow. Lou, how far away can you see? I mean, because Dan, obviously you're talking about seeing, distant galaxies. How far away can you see individual stars?
Well, generally, you can't see them. You can't resolve them beyond our local universe. They're hard to see. In fact, when you look at these collections of stars, or you look at these galaxies, they themselves are collections of stars.
Right.
hundreds of billions of stars that are so unresolved they just look like a single object. But every once in a while, through the power of gravitational lensing, we get lucky. And sometimes, by the nature of where these objects are moving through their space and how the nature of the lens is, we might get a magnified star. If we look at slide 8, please. So this was an example found in the same data set that we found our supernova in, of a individual star. It appears to be an individual star that was lensed by this foreground lens, and so magnified that we actually could see just the one star being shown to us through the nature of the lens. It's a really cool effect. It's really, it seems kind of subtle when you see all these other knots along the galaxy. Those are actually large star-forming regions of collections of thousands of stars. This individual star is momentarily magnified to be as bright as all those collections of stars.
Wow, that's amazing. Yeah, to think that one big light was, so many stars, and that one was a single sun. That's incredible. Dan, let me ask you, how can astronomers learn more about these distant stars and galaxies?
Well, we're very excited for the James Webb Space Telescope. If you show slide 4, this is scheduled to launch next year. You can see it here compared to the Hubble on the left, and the James Webb is on the right. You can see Nancy Grace Roman for scale there. The Hubble is about 8 feet in diameter, so about the size of your ceiling, give or take. You could picture it in your room. And James Webb is going to be 6.5 meters, so 20-something feet. And with that bigger mirror, we'll be able to see farther. It also has a lot more capabilities that Hubble didn't have. So I mentioned we've seen 97% of the way back to the Big Bang. Well, now we'll be able to see that first 3% of cosmic history where we've yet to see what a single galaxy looked like. And not only galaxies, but as Lou just showed, we'll be able to see individual stars in the beginning of the universe, and we'll be able to study them and understand what they were like. In the very early universe, there was only hydrogen and helium. So we'll see if stars and galaxies were just made of those primordial elements, or if the supernovae had gone off and started producing the stuff of life very early in the history of the universe. And so understanding, it really gets to our origins and how we got here, the whole process. So we're very excited.
Okay, wow. So that lens is much bigger.
That's right.
It's fascinating what you guys are talking about. I guess that's why they call it space-time. The distance that we can see takes us farther back in time. That's
right.
That's exactly right.
Hence the name, space-time. That's incredible. There's one thing that I was thinking about, Lou, when you were talking about how it distorts and magnifies and can sometimes multiply the image. I was like, wait, are you guys sure that there are this many stars and that they're not all just multiplied? Maybe there's like 6 of them. But through gravitational lensing, everything's just being multiplied 2 billion.
We're pretty sure there's more than 6. We have a pretty good idea there's more than 6. However, you may have a valid point. There may be, things that we will learn as we begin to look at more of the universe, both more deeply and covering the entire sky. I doubt that we will cover that, this side of the universe looks like it's replicated over here, but, who knows?
No, but I love the fact that, what you were talking about being able to predict, because that's how because you do the calculations, you realize, okay, well, if it were the same star, it would show up here, but wait, let me, for anybody watching who missed the beginning of the show, and because I was going off on a little tangent there, but if you're just joining us, we are talking with Lou Strolger and Dan Coe about how astronomers use the lensing of light by the gravity of clusters of galaxy to study the distant universe. Now, I think we have some audience submitted questions. Oh, yes, we do. This question is from HR, and his question is, does lensing effect appear only in visible wavelength, or does it appear on all wavelengths? That's a very good question.
Very good question.
Who wants to take that? Lou, Dan?
Should I?
Yeah, I go. Yeah, go ahead, Dan.
Go All right. Either way, we would both give the same answer. It affects all wavelengths. It lenses them all equally. So it doesn't change the color of distant objects, for example. It just really makes them brighter and bigger.
Oh, okay.
Yeah, it's the one thing that's different about gravitational lensing than your piece of glass lensing is that there is no chromatic effects, right? With regular lenses, you can possibly have a different focal point than an optical in blue, for instance, than in red. That's not true for gravity. Gravity bends it all in the same way.
That makes sense, especially because we were talking about before how it bends matter and dark matter, and so it makes sense that it would affect everything, in similar pattern way. We have another audience question from Sean Aurora. How is it even possible how they can see this far? Aren't there obstructions like asteroids or space junks or planets? And Sean doubled up on the questions. What we see from Earth when we look up are called stars. Oh, this is a good question. Does that mean the stars we're seeing from the ground are actually galaxies, billions of suns? Lou, you want to take that one?
Yeah, I'll take the first part.
Maybe you guys can split them up.
Yeah, the first one's easier, and I'll take it. Space is really, really big, is the bottom line. There's a lot of empty space out there. I can't even begin. I'm hesitating to try and come up with an example for fear that I might get it wrong. But there is a lot of space out there. You could look along any line of sight and be free from looking at things within our own galaxy. And that's great for the most part. So yes, there are lots of things out there that we know of, space junk, planets, satellites of different types. But we are largely free of those obstructions. Now, every once in a while, they do appear in our images, and one person's trash is another person's treasure, and they are really interesting when they do. But for the most part, we have an unobstructed view of most of our universe.
I mean, Lou, is it the case that, if something is in space, like junk or a planet, it's moving? So it wouldn't be a constant obstruction. And also probably the telescopes in space are moving as well.
Dead on, yes. Yeah, so things that are closer to us tend to move a little faster. So, satellites that orbit the Earth leave this long trail that go through our images. There are satellites that orbit beyond the orbit of Hubble, so sometimes that happens. There are lots of small asteroids and small cometary minor planets that exist in our solar system, and they do pass in our images, and we can see them on exposure times on time scales of only a few seconds. We can begin to see them move. In our own galaxy, there are certainly stars that we sometimes see that are so faint and so distant that we wouldn't ordinarily identify them as stars. We can, with some analysis, identify them as stars, but they look like they could be, on first glance, anything like any background object. But when you come back and look at the same frame a day later, that object is subtly moved. So, yes, we can identify them by their motion as well.
So basically, you guys don't just look once and then make an assumption. It
takes time to accumulate the depth that we see, and sometimes that's done simultaneously. Or all in one sequence. That's usually very, very rare because it takes the telescope has to orbit the Earth, and as it does, the Earth occults the observation. So you have to break up your observations into visits, and sometimes those visits happen sequentially. Most of the time they don't. They get scheduled over years.
Right. Dan, did you want to take the?
Yeah, sure. These are
or galaxies.
Yeah, these are great questions here, and I'll say that every time that Hubble takes an image, it's the size of a grain of sand held at arm's length. So a very small piece of the sky. And when we look for long enough, we see thousands of galaxies, and in every galaxy there are billions of stars. And so at some point somebody did the math, and I forget what they came up with, but there's billions of galaxies that we could see over the whole sky. Each one of them has billions of stars. So there's trillions and trillions of stars just in the universe we could see. I mentioned we can see back to close to the Big Bang. The universe might be much bigger, even beyond that, to places that we will never be able to see because the light simply hasn't had enough time to reach us. I mean, maybe you wait a few billion years and more of the light will get here, but the universe is immense.
Yes. I'm not waiting that long. Now we have another question here from Cheryl Mitchell. Oh, is your telescope on satellite or Earth? I'll let you guys answer that one, even though I think I could answer this one.
You might have the answer. Hubble is a satellite. It's a satellite which orbits us once every 90 minutes, and in low Earth orbit. So it has the benefit of being outside the Earth's atmosphere for seeing distant objects without both the distortion that our atmosphere brings, and the atmosphere protects us from harmful radiation, from harmful UV radiation. But that actually is a very interesting wavelength for studying most energetic objects in our universe. So Hubble gives us an unobstructed view without that distortion from the atmosphere. And without and gives us a clear picture of everything from the ultraviolet all the way through to the near infrared.
Now, that actually brings up a question. Back to our topic about gravitational lensing. Do you need space telescopes like Hubble and the upcoming James Webb telescope to see the lensing effect?
No, there's been plenty of lensing observed from the ground, and the ground-based telescopes, they've covered a lot more of the sky. Like I said, Hubble has a very small field of view. There is another telescope upcoming later after James Webb, the Roman Space Telescope, which will cover more of the sky. But until then, the ground-based telescopes have covered the whole sky to the point where they've seen the brightest things that have been lensed over the whole sky, which is very exciting. Then we go back with Hubble and study them in more detail. They also can collect, they're bigger on the ground, the big ones can collect more light and spread it out into a spectrum, so we can analyze what kind of chemicals are in the galaxy and learn a lot more about them.
Okay, now this is just a question for me. Hubble and James Webb, are they going to be in the same orbit?
No, Hubble will orbit the Earth, but James Webb is going to orbit a point that sits just 4 times the distance from us to the moon. It's a unique gravitational spot called the Lagrange point 2, but it essentially orbits the sun with the Earth. So we'll have a different set of we'll be able to do more with it than we are capable of doing with Hubble for many reasons, but its position in the sky is another big benefit to being able to see more of the sky and see it more often.
Okay, wow. Okay, that it's funny because on the show we've talked a lot about James Webb, but that's the first time I've found out that it's going to be in a different place. All right, here's one for both of you guys. What's next in your quest to study the faraway universe? With these amazing gravitational lenses. Dan?
Yeah, as a matter of fact, we just submitted proposals to use the James Webb Space Telescope, and we're going to find out in, I think, February or March, the results of that. A bunch of astronomers, usually they would convene in Baltimore to discuss them, but with the pandemic, it'll be done virtually. So we'll see. If you bring up slide 9, I could show you. We have kind of a friendly competition between the lensing and the blank fields, and so I think that lensing will be the key to discovering the first galaxies with James Webb. And you see on the right here, we've zoomed in. It's not really obvious because you're looking at a smaller area of the sky. So you're sacrificing some area that you're searching for that's being magnified. But there are so many small, faint galaxies in the early universe that come into view that I think we're going to win. I mean, in practice, we're going to do both. We're going to look at blank field, we're going to look at lensing, and it'll be fun to see what we see.
Wow, gravitational lensing as sports ball metaphor. Okay. Lou, what's next for you?
So I'm still keen on observing supernova. Our big goal, of course, in our community is to better understand these tools, which tell us a lot about the cosmic distance scale and the constituents of our universe, how much matter there is, whether or not that be ordinary or dark matter. And of course, this new, rather mysterious, but very large component of our universe called dark energy. We're trying to understand the nature of really what dark energy is doing to the change how we perceive distant objects. This will be done by looking at more and more supernovae collected through large campaigns with Dan already mentioned the Roman Space Telescope. That will be integral to doing a lot of this. But I'm also keen in looking at these clusters because, as Dan said, they open up opportunities for finding the more distant objects and hopefully learning a lot about the distance scale through that.
Oh, wow. Fantastic. All right. Well, since we're not far enough away for gravity to distort our time, we're running out of it. So before we finish up, though, do you guys have any final thoughts that you'd like to share with the audience?
Go ahead, Lou.
Oh, Lou?
Well, so I'm really happy to be here. I'm glad that I could talk a little bit about the stuff that I'm really, really interested in. I hope that we'll have great opportunities with the next space telescopes, the James Webb Space Telescope and the Roman Space Telescope to be coming very shortly thereafter. And I'm excited about our opportunities.
Right on. Dan?
Sure, and if people in Baltimore or elsewhere are interested in our institute, there's plenty of opportunities for jobs as astronomers, engineers, programmers, a lot of different things. And I also wanted to say, this past year has been extremely difficult, but it's been a good week for science. There's been a lot of scientists who worked really hard and developed vaccines for us that just rolled out. Right. So hang in there. Try to enjoy the holidays, and remember, this lap around the sun is nearly over.
Around this sun.
Yeah.
Excellent.
That's right.
Dan, Lou, thank you both so much for being here and sharing your expertise. And for the audience, thank you so much for joining us and learning, along with me, about using lenses of clusters of galaxies to study the universe. Now, you can see the video that we just did, as well as all of the other Universe Unplugged videos at universeunplugged.org. And there's some other great, incredibly smart astronomers, just like these guys. It's in other shows. And you can always click on this link here to see this show and those. Or you can subscribe on YouTube, and you'll be the first to know when our next one comes out. And follow us on Facebook to catch the live show. And until that next one, I'm Phil Lamar, along with Lou Strolger and Dan Coe, and this has been Ask the Astronomers Live. Thanks for watching.
Thank you.
Thanks, everybody. Take care.
Take care.